For 182 days straight, this object has been defying one of the most fundamental rules of comet physics. Its thrust hasn't decreased, not even by 1%. Every other comet in recorded history shows thrust decay. Every single one. But not this one. And that's just the beginning. Because what astronomers are discovering about this interstellar visitor is challenging everything we thought we knew about how comets behave. If you want to see the evidence that's making scientists question their textbooks, hit that like button and let's examine the data. Because what I'm about to show you is going to change how you think about what's possible in our solar system. Over the past several months, something extraordinary has been unfolding in our solar system. Astronomers and independent observers around the world have been meticulously documenting 3I Atlas, this ancient interstellar traveler that wandered into our cosmic neighborhood from the depths of space. And with each new observation, with each new data set, with each new high-resolution image, this object has challenged our expectations in ways that are becoming increasingly difficult to explain with conventional comet physics. Each anomaly by itself would be noteworthy. Unusual, certainly, worth publishing a paper about. But when you start stacking them together, when you see all of these impossible behaviors occurring simultaneously in the same object, that's when scientists start asking uncomfortable questions. Let me walk you through what we're seeing, because the latest findings are the most surprising yet. We have the longest and clearest images of its tail ever captured. We have the most stable rotational behavior ever measured in any comet, anywhere. We have a complete, total absence of thrust decay that defies over a century of cometary science. We have unusual shiny surface patches that reflect light in ways comet surfaces simply don't. And we have rhythmic cyanogen bursts, sharp blue beams of gas that appear on a precise clockwork schedule tied directly to the object's rotation cycle. Let's start with the image that captured worldwide attention and sent ripples through the astronomical community. Astrophotographer Satoru Murata accomplished something remarkable. Using a relatively modest 0.2-meter telescope that's only about 8 inches in diameter located in New Mexico, he captured what many experts are calling the best, highest quality image of 3I Atlas obtained so far. The technique he used was meticulous. He combined 24 separate exposures, each lasting 60 seconds, and then processed them together to create a single, incredibly detailed composite view of the object. And what that image reveals is absolutely stunning. Multiple jets of material are clearly visible, pointing in different directions. Some jets aim toward the sun, which is expected, but others point away from it, which is far more unusual. The image shows a sharp anti-tail, a phenomenon where material appears to stream toward the sun rather than away from it. And most impressively, it reveals a remarkably long, narrow, and tightly collimated tail. How long? More than 2.6 million kilometers. That's 2.6 million. To put that in perspective, that's roughly 7 times the distance between the Earth and the Moon. Imagine drawing a line from Earth to the Moon, then doing it 6 more times, and you'd still be measuring the tail of this object. But length isn't what makes this tail extraordinary. Many comets develop long tails. What makes this one special is its structure. The tail remains narrow, incredibly narrow. For millions of kilometers, it maintains this tight, column-like structure instead of spreading out into the broad, diffuse fan shape that normal comet tails develop. This image matters tremendously because it captures the structure of 3I Atlas in a way that allows scientists to analyze multiple aspects of its behavior simultaneously. The anti-tail structure, the tail alignment, the particle distribution, the jet patterns. Everything is visible in unprecedented detail. It's like upgrading from a blurry security camera to a 4K video. Suddenly, details that were hidden or uncertain become crystal clear. Now, let me tell you about the finding that has scientists completely baffled. 3I Atlas has shown 0 thrust decay for 182 consecutive days, 6 full months, half a year of continuous observation with the same result every single time. 0 decline, 0 decrease, 0 weakening. Let me explain why this is so profoundly strange that it's forcing scientists to question fundamental assumptions about cometary physics. In comet science, there's a parameter called A3. It's the non-gravitational acceleration parameter, and it measures how much thrust a comet generates from outgassing as it releases material into space. Think of it like measuring the power output of an engine. For every comet ever studied, and I mean every single one, this parameter decreases over time. Always, without exception. As a comet moves away from the sun, the solar heating decreases, the surface temperature drops, the internal gas pressure falls, and the thrust naturally, inevitably fades. It's one of the most consistent, reliable patterns in all of planetary science. Astronomers have examined more than 1,200 comets over the past century, 1,200 different objects spanning every type, every composition, every orbital configuration. And every single one of them showed thrust decay between 20% and 50% as they moved away from the sun. Every single one until now. For 3I Atlas, the thrust has remained completely, perfectly, impossibly stable for half a year. The graph is flat. No decline whatsoever. This already makes 3I Atlas unique among all known comets in recorded scientific history. It's not just unusual, it's unprecedented. It's the kind of outlier that makes scientists either question their instruments or question their theories. When we see this kind of stability, when we observe behavior that violates what we thought were universal rules, we're forced to ask some very difficult questions. What kind of material composition inside the nucleus could possibly support this behavior? What kind of internal structure would allow sustained outgassing with zero thrust variation over such a long period? One possibility that scientists are considering is that the comet's interior is extraordinarily rich in supervolatile ices, materials like carbon monoxide or molecular nitrogen. These substances sublimate. They transform from solid to gas at extremely low temperatures, much lower than water ice. If the nucleus contains high concentrations of these materials, they could continue releasing gas steadily even as the distance from the sun increases and the available solar energy drops. The pressure could remain constant because these ices don't need much heat to vaporize. Another possibility is that the internal structure of the nucleus has developed stable vents or deep fractures that act like natural pressure regulators. Channels that funnel gas from deep reservoirs to the surface in a controlled, steady flow rather than in chaotic bursts. But even these explanations feel insufficient when you consider the next anomaly, because the mystery gets even deeper. Even though this comet is experiencing such strong and continuous outgassing, even though it's blasting material into space at a rate that should be creating significant forces on the nucleus, its rotation remains remarkably, almost impossibly steady. The rotation period has been precisely measured at 1616 hours. That's how long it takes for the object to complete one full spin on its axis. High-resolution monitoring through the Hubble Space Telescope, using some of the most sensitive instruments humanity has ever built, shows that the object wobbles by only 0.1 degrees over 4 full days of continuous observation. 0.1 degree. That's almost nothing. That's like watching a spinning top maintain perfect balance for hours on end. For a comet experiencing continuous, powerful outgassing from multiple jets, this level of rotational stability is extraordinarily unusual. Borderline impossible, actually. Here's why. When jets blast material off the surface, they create forces. Those forces push on the nucleus unevenly because the jets aren't perfectly symmetrical. They're not perfectly balanced. And those uneven forces create torques, rotational forces that should cause the nucleus to tumble, to wobble, to drift off its axis over time. Every comet we've ever studied shows this behavior. The rotation becomes irregular. The wobble increases. The spin axis shifts. It's inevitable physics. But 3I Atlas remains stable, locked in, perfectly consistent. This stability suggests one of two possibilities. Either the outgassing forces are somehow perfectly balanced in a way that naturally cancels out all torques, which would be an extraordinary coincidence, or the internal structure of the object is absorbing these forces in some way that prevents wobbling. Neither explanation is particularly satisfying because both require very special, very unlikely conditions. And now we arrive at one of the most visually striking and scientifically puzzling discoveries. Observers have detected bright, shiny patches on the surface of 3II Atlas. These reflective areas are not subtle. They're not barely visible. They're 20% brighter than the surrounding dusty terrain. The numbers tell the story. These patches have an albedo, a measure of reflectivity, of 0.25. That's compared to the average surface albedo of 0.15. They're reflecting significantly more sunlight than the rest of the surface. And here's what makes them even more intriguing. These reflective areas remain fixed relative to the rotation. They're not moving around. They're not temporary bright spots that appear and disappear. They're permanent surface features locked to specific locations on the nucleus. For comparison, most comets have extremely dark surfaces, like coal, like charcoal, blacker than asphalt. Typical comet surfaces have albedos around 0.4 to 0.6. They absorb almost all the light that hits them. When a comet shows reflective regions, when we see bright patches like this, it usually means one of two things. Either there's exposed water ice on the surface that hasn't been covered by dark dust yet, or there are compact crystalline materials, minerals with smooth surfaces that reflect light efficiently. But both of those explanations create their own problems. Exposed ice should sublimate quickly under sunlight, covering itself with dust and darkening over time. And crystalline minerals should be rare on comet surfaces, which are typically covered in loose, irregular dust particles. So what are these shiny patches? Why are they so bright? And why do they remain stable over time instead of changing as the comet rotates and different areas get heated by the sun? Nobody has a completely satisfying answer yet. But wait, there's more. Because the next anomaly is perhaps the most fascinating of all. Observers have detected rhythmic cyanogen bursts emanating from 3I Atlas. These aren't ordinary gas releases. These are sharp, focused beams of CN gas that appear with precise clockwork regularity. Cyanogen, or CN, is a common component in comet atmospheres. It forms when sunlight breaks apart complex organic molecules on the comet's surface. Most comets release CN gradually, creating a diffuse cloud around the nucleus. But 3I Atlas is different, very different. These CN emissions appear as sharp blue beams. They're narrow, they're collimated, they're focused like searchlight beams cutting through space. And here's the key detail. They show no associated dust. They're pure gas jets with no solid particles mixed in. That's highly unusual because normal comet jets carry both gas and dust together. The gas drags dust particles along with it as it escapes. But these CN bursts are clean, pure gas with no contamination, and they occur on a schedule, every 16.2 hours, exactly matching the rotation period of the nucleus. This isn't random. This isn't chaotic. This is synchronized behavior that indicates these gas bursts are coming from a specific area on the surface, a particular vent or opening that becomes active whenever it rotates into direct sunlight. The timing is so precise that you could set your watch by it. Every rotation, like clockwork, the burst appears. The visual appearance of these CN spikes has led some observers to describe them as looking like blue laser beams. Now, they're obviously not actual lasers. Lasers require specific quantum mechanical conditions that don't exist naturally in space. But the narrow, collimated nature of these gas beams, the fact that they remain tightly focused instead of spreading out, makes them look visually similar to laser light. This level of collimation indicates that the gas is being ejected from extremely narrow vents, tight channels or cracks in the surface that focus the flow like a nozzle, like spraying water through a thin tube instead of just splashing it randomly. But here's what puzzles scientists. Natural vents and cracks should widen over time as the gas flow erodes the walls. They should become irregular. They should start producing broader, more diffuse jets. These CN beams aren't doing that. They're maintaining their narrow structure, their precise timing, their consistent behavior. It's behavior that's difficult to explain through purely natural processes. Now, let's talk about the tail again, because there are additional details that make it even more remarkable than just its impressive length. The tail of 3I Atlas stretches more than 2.6 million kilometers into space, and new observations suggest it continues to grow longer with each passing week. A tail of this length isn't necessarily rare by itself. Several bright comets throughout history have developed tails that stretched for millions of kilometers. Comet Hale-Bopp, Comet Hyakutake, Comet McNaught, all of them produced spectacular tails visible even to the naked eye. What makes the 3I Atlas tail unusual, what makes it scientifically significant, is that it remains narrow for such an enormous distance. Normal comet tails spread out, they diffuse, they fan out into broad structures as the particles disperse. But this tail maintains its tight linear structure for millions of kilometers. This suggests something very specific about the particles inside the tail. They're being influenced by an extremely organized flow pattern. If the particles were large and heavy, they would fall behind quickly and spread out along the orbit. If the particles were small and light, they would be pushed by solar radiation pressure into a broad fan shape, creating the classic curved tail structure we see in most comets. But the particles in the 3I Atlas tail appear to form a tight linear column. They're staying together, moving in parallel paths, maintaining formation over vast distances. That requires a very specific size distribution and a very uniform ejection mechanism. Both are difficult to achieve through chaotic natural processes. Next, let's examine the anti-tail, because it's showing behavior that extends beyond what's normally observed. An anti-tail is an optical phenomenon that appears when Earth crosses the orbital plane of a comet. Large dust particles, too heavy to be pushed away by solar radiation, remain close to the comet's orbital path. When Earth passes through that plane, we see those particles edge on, and they appear to point toward the sun rather than away from it, creating the illusion of a tail going the wrong direction. This phenomenon usually lasts for a brief period, a few days, maybe a week, just long enough for Earth to cross through the particle plane. But in 3I Atlas, the anti-tail remains sharply defined well beyond the typical time frame. It's persisting, staying visible, maintaining its structure longer than it should. This suggests that the comet is continuously releasing unusually large particles, or that the release mechanism is highly directional, concentrating particles in the orbital plane rather than spreading them in all directions. Again, this is possible through natural means, but it requires very specific, very unusual conditions. So let's step back and consider what we're looking at. Let's examine the full picture. We have zero thrust decay for half a year. We have near-perfect rotational stability despite powerful outgassing. We have reflective surface patches that remain fixed in place. We have rhythmic collimated cyanogen bursts on a precise schedule. We have an extremely long, narrow tail. And we have a persistent anti-tail structure. Scientists are now considering three main hypotheses to explain this constellation of anomalies. The first hypothesis is the natural explanation. This is the default position, the one that most scientists start with because it requires no extraordinary assumptions. Under this scenario, 3I Atlas has a unique, perhaps even extreme, but still natural mixture of volatiles and structural characteristics. The nucleus may contain unusually high concentrations of carbon monoxide or molecular nitrogen ices that sublimate consistently across a wide temperature range, explaining the stable thrust. The stable rotation might indicate that the nucleus is unusually dense, or that it has a rigid internal structure that resists torques, or that the mass distribution is perfectly balanced by chance. The shiny patches could be areas where fresh ice has been exposed by recent fractures, or where crystalline minerals happen to be concentrated on the surface. The CN bursts could emerge from deep, narrow fractures that channel gas from interior reservoirs, with the timing controlled simply by which areas face the sun during each rotation. In this explanation, every single anomaly has a natural cause that fits within the established physics of cometary science. It would make 3I Atlas an extreme outlier, yes, a statistical rarity, but still fundamentally a natural object. The second hypothesis focuses on observational limitations and geometric effects. Some of the apparent stability or consistency might result from the specific geometry of how we're observing the comet. The angle between Earth, The comet's orbit and the sun can create optical effects that make structures appear sharper or more organized than they actually are. The lack of variation in thrust measurements might be influenced by the sensitivity limits of our instruments. Perhaps there is thrust decay, but it's too small for us to detect reliably with current technology. Some of the periodic behavior might appear more synchronized than it really is, because our data consists of snapshots rather than continuous monitoring. We're taking pictures every few hours or every few days, and we might be missing variations that occur between observations. Under this explanation, the anomalies might be less dramatic than they appear. They might be artifacts of how we're measuring and interpreting the data rather than genuine physical mysteries. The third hypothesis is what some are calling the engineered scenario. Let me be absolutely clear about something. This is not a conclusion. It's not a claim. It's not even a strong suspicion. It's simply a hypothesis that some researchers are considering because the behavior of 3I Atlas is more stable, more organized, and more precisely controlled than any known natural comet. In this scenario, the jets might be functioning like directional thrusters rather than random outgassing vents. The CN bursts could be interpreted as controlled gas releases rather than passive sublimation. The shiny patches might represent surface areas with deliberately different materials or even active reflectors. The zero wobble and zero thrust decay might indicate some form of active stabilization system rather than lucky geometry. The narrow, collimated tail might result from precisely controlled particle ejection rather than chaotic venting. Again, and I want to emphasize this strongly, there is no proven evidence for this interpretation. No spacecraft has visited 3I Atlas. We have no direct measurements of its composition beyond spectroscopy. We have no images detailed enough to see surface structures. However, considering this hypothesis, even as an unlikely possibility, serves an important scientific purpose. It forces researchers to examine all the data with fresh eyes. It encourages careful analysis. It prevents premature closure around comfortable explanations. And it ensures that if something truly extraordinary is happening, we won't miss it because we assumed it couldn't be real. So what happens next? How do we resolve these mysteries? As 3I Atlas continues moving along its orbit, approaching its closest point to the sun, observatories around the world are preparing for intensive observation campaigns. The key objective is to gather the highest resolution data possible during the most active phase of the comet's evolution. Scientists will measure the velocity of gas and dust particles with unprecedented precision. If the CN bursts show ejection speeds in the hundreds of meters per second range that would support natural sublimation processes, but if the speeds reach into the kilometers per second range, that would require scientists to develop entirely new models to explain the acceleration mechanism. Spectroscopy will reveal the exact chemical composition of the jets. Is it just water and simple molecules, or are there unusual compounds that might indicate exotic interior chemistry? High-resolution imaging campaigns will track how the shiny surface patches evolve over time. Do they stay fixed? Do they change? Do new ones appear? Do old ones fade? Researchers will analyze whether the thrust remains stable beyond the current 182-day record. Will it eventually decay like every other comet, just much slower? Or will it remain flat indefinitely, continuing to violate what we thought were universal rules? In the coming weeks and months, scientists will study the tail structure, the anti-tail geometry, and the jet patterns to see if they change as the comet gets closer to the sun. They'll monitor whether new jets appear or whether existing jets weaken or strengthen. They'll remeasure the rotation to confirm whether the wobble truly remains impossibly small. Every new observation, every new data point will either support conventional explanations or push us further into unexplored territory. Now let's take a moment to consider the broader context of what we're witnessing. 3I Atlas is only the third confirmed interstellar object ever observed in our solar system, the third visitor from beyond, the third traveler from the vast darkness between the stars. The first one, Oumuamua, showed completely bizarre behavior, unexplained acceleration without any visible tail or outgassing, a cigar-shaped or pancake-shaped geometry unlike anything we'd seen. It violated expectations so dramatically that it sparked debates that continue to this day. The second one, 2I Borisov, behaved much more like a standard comet. It had a tail. It outgassed normally. It followed predictable patterns, but even Borisov contained chemical signatures that differed from typical solar system comets, hinting at different formation conditions in its home system. Now, 3I Atlas is presenting us with an entirely new series of anomalies, different from Oumuamua, different from Borisov. A unique pattern of behaviors that challenges assumptions in different ways. Each observed feature, each measured anomaly, gives us clues about the diverse environments in which interstellar objects form, about the conditions in other stellar systems, about the variety of planetary formation processes occurring throughout the galaxy. Whether the ultimate explanation turns out to be natural, whether it involves unusual but conventional physics, or whether it points towards something that goes beyond our current understanding, 3I Atlas is providing scientists with an extraordinary opportunity. An opportunity to learn about materials and processes from other star systems, to test our theories against objects that formed under completely different conditions than anything in our solar system, to expand our knowledge of what's possible in the universe. This object is demonstrating that the diversity of interstellar visitors may be vastly greater than we ever expected, that each one will surprise us, that each one will teach us something new. The story of 3I Atlas is still actively developing, still unfolding in real time, and the next few months will be among the most important observation periods in modern cometary science. The closer this ancient traveler gets to our star, the more detail we'll be able to see. New images will reveal surface features. New spectroscopic data will map chemical distributions. New brightness measurements will track activity levels. All of this information will refine our models, test our hypotheses, and hopefully solve at least some of these mysteries. But even if we find natural explanations for everything we're seeing, even if every anomaly turns out to have a conventional cause, the journey of discovery will have been worth it. Because 3I Atlas has already taught us something invaluable. It's taught us that the universe is far stranger, far more diverse, and far more surprising than our textbooks suggest. It's taught us that interstellar space can preserve objects in ways we didn't fully appreciate. That processes we thought were universal might have exceptions. That visitors from beyond our solar system will continue challenging our assumptions and expanding our understanding. So what do you think is really happening with this extraordinary object? Is it an extreme natural phenomenon that pushes the boundaries of what's possible? Is it revealing gaps in our understanding of comet physics? Or is there something more going on that we haven't even considered yet? Let me know your thoughts in the comments below. And if you want to follow this story as it continues to develop, as new observations come in, as scientists work to solve these mysteries, make sure you subscribe and turn on notifications. Because when the next breakthrough happens, when we finally understand what makes 3I Atlas so unique, you'll want to be among the first to know. The universe is full of mysteries, and right now, one of the most intriguing is making its way through our cosmic neighborhood, leaving scientists puzzled and excited in equal measure. Stay curious, stay skeptical, stay open to possibilities, and keep watching the skies, because the next discovery could change everything.